All right, welcome everybody. Today, instead of doing lab time, we kind of gave that lab time to Wednesday. You are going to have a lab time assignment today. We're going to learn today, though. We're going to learn about how to do separate compilation. When you start programming, you're used to your programs compiling very quickly, right? If you were to compile "Hello World," let's see here. Let's just pick something random. G++, cobalt.cc. If we time that, you can see it was time G++ cobalt.cc. It took a third of a second to compile. If we time G++ main.cc, it's 0.4 seconds. Main.cc is 88 lines of code. Cobalt.cc is 89. Like, trivial amounts of time to compile these things. But when you start getting into bigger and bigger projects, your code will take longer and longer to compile. And this is something that we hate, because what makes coding, what makes development really productive is when you can make a change quickly, compile it quickly, run it quickly, test it, get feedback, aha, that didn't work, go back, edit, save, compile, run. And you have that really tight development loop where you're constantly writing code and trying it out, and I passed another test case, great. When it takes 3 hours to compile your code, then you start coding differently. When it takes a long time, like even like what I notice is like when it takes like 10 or 15 seconds to compile a project, which is not like, all you have to do is include a header file, like CImage or something for image development. Just one header file adds like 10 seconds to the compile time. That's enough to make me not compile that often. Instead, I will write more code. Instead of writing 2 or 3 lines of code, saving, compiling it, testing it, running it, blah blah blah. Instead, I write more code, and then that causes more problems to build up. If you start writing 15 lines of code at a time between compiles, 30 lines of code, 100 lines of code, you're going to have so many bugs in your program that debugging it is then going to take forever. And each time you have to compile your code to debug it, that's also going to take more time because your compile time's long, and it just everything escalates, and it's terrible. So trying to minimize compile time is really important. So here is Easy Peasy. Easy Peasy is the pre-check program that we use. I've got a towel on my laps just in case Louis comes in here, but he's not blessing me with his presence today, so I put that aside. So you've got some CC files in here. We got some C++ files in here. All told, these files amount to 1,500 lines of code. Not a lot. But if I had to recompile all of them every time I modified anything, it would just take forever. Okay, even with just 1,500 lines of code, which is not very many. So let me show you what it looks like. I'm going to skip ahead a little bit. Let me show you what it looks like when you have your build system done properly. Let me go into, main.cc. It's 400 lines of code. And I'll add a comment, extra error messages. And then when I type make, I'm typing make, not G++ star.cc. I could compile like that, but I'm not going to because it would take forever. Instead, I'm going to type make. Make is a program that will intelligently build your project. In order for make to work properly, you've got to have something called a Makefile, which is what you guys are going to be doing during lab time today. You're going to be building your first Makefile. Before I show you what that looks like, let me just show you what it looks like when I type make. I've got, 40 or so files in here, but does it compile all of them? No, that's how long it took. So it recompiled main, and then it built the executable using all the .o files. Okay, so what is a .o file? Okay, so a .o file, you can think of a .o file. It's technically an object file. It's object code. But what you can think of an object file as really meaning is it's the results of the compilation of that source code file. So I've got my source code here, 400 lines of code inside of main.cc. And that main.o that it produced is the result of compiling just that one file. Technically, it's called a translation unit, because when you have a file that includes something, it pulls header files in and things like that. that whole expanded file is called a translation unit. The results of compiling that translation unit is this .o file here. And you can see that there's one of those .o files for every one of my .cc files. And as the result of that, instead of having to recompile all of my .cc files every time, I can just save the results of them. Because all I changed was main. I didn't change this guy. I didn't change this guy. All I changed was main.cc. So all I had to do was recompile that one file, which you can see right here, using Clang, standard library, C++ version 20, standard 20. Debugging turned on, optimization turned on, all warnings turned on except for unused variables and unused parameters. So instead of having to recompile 40, it only had to recompile 1. Then after and this -c here is what generates that .o file. Now your compiler always makes a .o file, it just deletes it afterwards most of the time. So with the -c there, you can think of -c as meaning partial compilation. It saves the .o file, and then when we want to build the a.out, the executable, you can see the next step here is it links together all of those .o files and puts them into an executable. And so if I were to edit a different file, like if I were to edit, I don't know, dref null pointer, this is a static analyzer. Okay, this one doesn't have a whole bunch of stuff in it. Not used. Let's just add a comment there. Whatever. If I type make again, you'll see it recompiles the dref null pointer file, makes a .o out of it, and then it puts all the .o files together to make our a.out. So if I say ls-l on dref null pointer, you'll see that I edited the .cc file, and then it built this 88k .o file out of this trivial .cc file. But it only builds that. And if I type make again, nothing needs to be done. So the build system looks at all of your source code files, figures out which ones have been updated just by looking at the timestamp. In fact, if I were to mess with the timestamp on something, Touch is a program that updates the timestamp. If I were to update the timestamp on, I don't know, incorrect cout.cc, and then I hit make, you'll see that it recompiles just that one file. Now, if I were to touch a couple files, incorrect cout.cc, incorrect cn.cc, these are all static checks for errors that students make. If I were to edit 2 files, which I'm pretending to do here by just changing their timestamp, if I were to hit make, you'll see that it compiles both of them. Compiles the first one, takes a little while, doesn't it? Compiles the second one, takes a little while, doesn't it? Then after that's finished, then it links everything together and builds the a.out. Hello, Louis. Kitty. He has blessed me with his presence. Hello. So, do you guys understand the benefit of this? So if I were to time, let me do a make clean. Make clean is going to erase all of the .o files. It's going to erase all of those saved results of compilations. It's going to erase the a.out. It's going to erase all the .o files. Watch how long this will take to run. Time make. So I'm just going to put this on the background because this is going to now rebuild my entire project. Make clean is a convention that you will see all throughout the computer science world that wipes out all of your executables and intermediate files and all that stuff, cleans everything out, and then rebuilds it all from scratch. Because sometimes your directory gets screwed up. Maybe your partner uploads files into your directory and the timestamps are broken on them, and you're just like, I can't fix this. It's too much effort. Make clean, make. And so that just rebuilds the entire project from scratch. You guys understand? Make clean. Good stuff. If you want to do a full rebuild, make clean and make is your go-to solution. So this is going to run for a while. So I'm just going to minimize this. Definitely saves time over the course of the project. Yeah, or just like when you're doing development. Like imagine you're working on, Microsoft Office or Microsoft Windows, and you've got thousands of files. Like it just takes a really long time to do a full rebuild. And so if you have make, or nowadays you have CMake, which is kind of the industry standard. CMake oftentimes just makes a Makefile for you, which is sometimes really useful, and sometimes you might as well just use a Makefile. Kind of depends on your circumstances. CMake is kind of the industry standard nowadays. And then you can have things that make CMake files, which make Makefiles for you, do the build for you. But at the end of the day, you need to have some sort of build system that figures out which files need to be recompiled and then put them all together into an executable at the end of the day. So that is what you're going to be doing in lab time today. You guys are going to be making a Makefile. Your first Makefile. Okay. So we're going to go over how programs get compiled, and we're going to talk about Makefiles, in particular, the syntax of a Makefile. How do you make the Makefile that controls the build process? Okay, so let's start off by talking about how compilation works. Okay, so you guys have all seen hashtag include, pound include, octothorpe include, however you want to put it, right? And what that does is it copies and pastes an entire file into your file. And you have to be a little bit careful with this for two reasons. First of all, there's a performance reason. And the performance reason is, to be careful with this thing, is that if you copy and paste too much, especially stuff that you don't need, your compilation time will slow down. CImage, like I said earlier, CImage is 100,000 lines of code. And so on our server, it'll slow down your compilation time by about 10 or 15 seconds. And if you're not using it, then you've just slowed down every compile you do by 10 or 15 seconds for no point. So you have to be careful to only include the things that you use, which is why on the new server, it'll actually give you a warning if you include a file that isn't being used at all. So that's a really fun warning. And so if you're ever including something you're not using, comment it out or delete it, and that'll speed up your compile time, depending on how big the include is. Okay, so the other issue you have to be careful of with hashtag include is if you include something twice. And the reason for this is because C++ has something called the ODR, the one definition rule. And if you declare something twice, even if it's identical, C++ gets mad at you. So if you say integer x semicolon, integer x semicolon, C++ is like, we've already seen Mr. X before. You cannot reduplicate him. He's already been defined in the current scope. And so if you were to say include a file and include a header file that has a class in it or something, and you include it again, now you've redeclared it and redefined, and C++ gets mad at you. So there is something that we put into header files. At the top of every header file, we typically will put hashtag pragma once. And that means if you try including this file a second time, don't. That is the pro gamer way of doing it. Hey, it finished. The more proper way of doing it is to, let's see here, color.h. Oh, this one doesn't have it at all. I am not using that file. That's why. Vim bug.h. I wonder if that is included. Yeah. This is the more proper way of doing it. So this is the pro gamer way. It's simple, it's easy. You just put this line, hashtag pragma once, at the top of your header file. And then what this does is it prevents the compiler from including it twice. And normally people aren't dumb enough to do something like this, right? Like people normally don't, people normally don't do this. Like they normally don't, copy and paste, hashtag include IOString 5 times. But what will happen is you include something, and then that thing includes another thing, and then some other thing you includes the same thing. So for example, if I were to hashtag include string like this, IOStream includes string, and fstream includes IOStream. And so if I, just with these three lines here, this would actually include the string header 3 different ways. String, directly, IOStream, which includes string, and fstream, which includes IOStream, which includes string. String. Yes. I think I said that right. If not, you know what I mean. So, so these things all have, if you go to them, let's see if we can do this. Go to definition. Yeah. I'm not in Vim. I don't have it set up on this. No. But anyhow, if you were to open up these header files, you will see either a hashtag program once, or more likely you're going to see this. These things should not be underlines, by the way. It should be just like Um, this does the same thing as the pragma once. And so what this is saying is that if we have never defined this symbol, if we have never defined the word work bug H before, and all of these words have to be unique, by the way, which is why I don't like if and defs. Because you have to come up with a different word for everyone. Typically it's the file name, but then, what if you have two files with the same name in different directories, then things break. Pragma once, to me, is more reliable. But Pragma once has its own problems. If you're on a network drive and things like that, sometimes the compiler can't figure out if this file is the same as this file, like if you're accessing it through shortcuts and things like that. So anyway, so this is the more proper way of doing it. So if and def work bug H, then we will hashtag define work bug H. And so if it gets included a second time, this symbol has been defined. This is false. It skips over everything until the bottom of the file where we have a hashtag indiff. And you also have to remember the hashtag indiff at the bottom of the file. If you forget that, everything breaks. If you have two different words here and here, everything breaks. If you have two different header files that have the same word here, everything breaks. And that's why I'm saying I actually prefer hashtag pragma once, even though if you look at the received wisdom on the interwebs, they will say you should do it the proper way, like this instead. So word to the wise, most people will tell you to do it like that. I have been burned enough times by these kinds of things. Like, like I said, the standard is usually you just give it the name of your file, folly.h or whatever. But if you have another file named folly.h in some other directory and they're included at the same time, they will cancel each other out. And I had that problem last night. No hashtag indiff. It didn't like it. It doesn't. Yeah, everything breaks if you forget it. Pragma once is just a one-line solution that has always worked for me. I've never had a problem with it. I have had problems with the standard header guard technology before, which dates back to the, Paleolithic era. Okay. So, if you have multiple files, two different CC files can include the same header file. We could compile this code by just saying g++ star.cc, but it's better to use a Makefile. A Makefile will say, hey, has imagine.cc changed? If it has, let's recompile it. If it hasn't, then let's just use the .o file from before because it hasn't changed at all. Okay, so let's talk a little bit about how compilation works to begin with. So you guys like this graphic? I photoshopped it myself. So, yeah, no, yeah, okay. So, thank you, I appreciate it. Okay, so step one in the compilation process is the preprocessor runs. Thank you. It is one of my finest works. So if we were to look at main.cc here, and we got this whole foo vector kind of thing here, move main.cc to public vector 10.cc. Okay. So that's our code from last time. If I were to make a new file and just make it just hello world, right? Or just make hello world. Okay, this looks like a one-line program, right? Maybe two if you count main somehow. If I were to compile this, it compiles very quickly, run it, hello world. If I were to word count the whole file, you'll see it's 6 lines of code, counting everything, spaces, and using namespace and everything. But what's actually happening behind the scenes here is after you've hashtag included IOStream, this thing turns into 44,000 lines of code. So the little hashtag include IOStream turns into 44,000 lines of code. That's why includes are painful, because we don't have a better system. Sort of modules are maybe the better system. Modules are not implemented yet. They came out in 2020. They're still not done. It's 2024 now. At some point, I'm sure people will finish it. But for now, we're stuck with this ancient build system from the 1970s. If I were to include cimage, let me locate cimage. cimage.h maybe. Where are you at? Okay, there we go. Okay, so if I were to include cimage, this little include cimage. Okay, so cimage turns it up to 121,000 lines of code, right? So if we were to just compile our code now, you just sit there and count, right? Just that one header file, you just see how long that thing adds to our compile time. Yeah. So yeah, even though I'm not using it, it adds substantially. Let's do time compile main.cc. Yeah. So this is with address sanitizer turned on, things like that. It's 4.3 seconds. We turn the optimizer on, g++-o3 main.cc. Turn the optimizer on this. It's going to have to chew over all the code. Actually, that wasn't too bad. 2.7 seconds. Yeah. So you physically age waiting for it. Yeah, and it just gets worse and worse. If you use Boost, if you use Bridges, any of these large libraries, their header files are extensive. They're massive, and you just it's like the Captain America aging, meme. You're just sitting there like looking at your code, like just physically, just wrinkles developing on your face as you do it. Yeah. Okay. So first step in the compilation process is the preprocessor does a pass over your code. It pulls in every time you hashtag include something, it copies and pastes the entire file in, and that just slows everything down. Yay. At some point, we're going to get modules. Modules have a good potential for speeding up the compilation process, but they're not out yet on G++. They are in Visual Studio. They're not on G++, so can't use them yet. Also, the standard library isn't modularized yet either, so someday, maybe soon, it'll be faster. Okay, so after the C preprocessor does its pass, the C++ compiler runs through the file. And mostly what a compiler does, the most important thing that a compiler does, is it keeps track of which functions and which variables exist and what's up with them, right? So if you say integer x, you know that there's a variable named x and it's of type integer. If you have a function called add, this add function here takes 2 integers as parameters. The names actually don't matter. It takes 2 integers as parameter and it returns an integer. And that's enough for anybody who wants to use this function to go ahead and compile. So what we put into header files is usually just things like this, that are just the name of the function, the parameter list, and the return type. And so a header file is actually much more compact than the full code most of the time. Cimage, unfortunately, puts all the code and all the standard header stuff into one file, which is why it's so massive. Most header files are just a list of function names that exist. So if we come over here and look at, I don't know, bug.h, you can see it's just mostly, this is what it looks like. This is what most header files look like. It is just, here's a function name, here's the parameter. Why are these things not const reference? Who wrote this code? And it returns a Boolean, all right? And so it has a list of function names, the return type, and the parameter list. The names actually don't matter. If you don't have the names there, it doesn't actually affect anything. And the reason for that is so that you can call them from another file. So even without knowing what these functions do, as long as you know what their name is, what their parameters are, and what their return type is, you can call them even though you don't actually know what they're going to do. It's like you can call square root, right? You can call square root without knowing exactly what square root's going to do, because you know square root takes a double as a parameter and it returns a double as a return value. That's all you need to know. When you're writing main.cc, all you need to know is that the name of the function, the parameter list, and the return type, and then you can use it. Later on, the piper comes calling, right? So if you were to, let's get rid of you, if you were to include cmath and you were to see out the square root of 10, it found it. It found the square root function. But what's inside of the header file might be nothing more than double square root. Here, let's make a new square root function. Let's call this square root 2 double x Do you see how I'm not getting a compilation error here? This code will compile just fine. But wait, you say, where is square root 2? Nowhere. It doesn't exist. So I'm not going to be able to build an a.out. It's not going to link. It's just what we're going to get to. But this code will compile just fine because the compilation step involves just you need to know the name of the function, the parameter list, and the return type. And so the compiler just goes through and just writes all these things down. And so here, when we're calling square root 2, it's like, hey, have I ever heard of a guy named square root 2 that takes a double and returns a double? Yes, I have. Okay, great. But if I were to change the name of this to square root 3, it's like, I've never met that man before in my life, and it won't compile. Okay? Do you guys understand this? So what the compiler mostly does is it just keeps track of, it has a giant table of all the different variables. And you can play friends with Addie, yes.
Can I play games with my friend Addie?
You can play games with your friend Addie, yes. You can use my phone to call.
Okay.
There you go.
I'm not playing friends with Addie.
You're going to pretend to be friends.
Yes. No.
Okay. So, but watch what happens if we try compiling this. So if I try compiling this, and I compile it with -c, remember -c is save the results of the compilation. It's separate compilation. If I were to compile this code with -c, it'll compile. No problem. What? Where's square root 2? Where's square root 2? You never wrote it. Yeah, it compiled just fine. It's fine because all you need to compile is the names need to match up. It checks the types. All the types work. If I try passing in, like hello world here, right? It won't compile because square root 2 doesn't take a string. It takes a double, and you can't convert a string to a double, so it won't compile. Okay. You guys understand? So you're like, but how's that compiling? Well, it compiles just fine. And if we look at the object file that we made here, you will see inside of here, it is calling a function called square root 2 that takes a double as a parameter. Remember, there's no variable name in there. And it is not found. That U there means we couldn't find it. It's not with us. I don't know where it is. Okay. Main does exist, right? Main is found in this file. So it's got a T there. It's in the text segment. The square root 2, though, is undefined. Okay. So the square root 2 is not found anywhere. And so if we try compiling this now fully without doing partial compilation, we're going to get what's called a linker error. Linking is the next step in the process. So the linker takes all of the .o files, and remember these .o files are made even if, like here, it actually makes a .o file. Look, right here. It made a .o file for me. It made a temporary .o file, and then it erases it. If you don't tell it to save the .o file, it generates a temporary one and then erases it afterwards. Okay. So if I were to try compiling g++ main.o, that's the linker step. It's the exact same thing. It's saying in function main, I'm calling this function square root 2. Function square root 2 does not exist. All right. You will also get a linker error if, let's comment this out maybe. You'll also get a linker error if you don't have a main. So if I were to compile this code, g++ main.cc. Sorry, there is no main.
Why is Louis in the house?
Why is Louis in the house? Because he sneaks in, girl. I can't stop him. So look at that. No, it's a linker error. This is not a compiler error. This is a linker error. LD is the linker. I'm getting a linker error. Oh, he is purring loudly. Okay. Okay, if you're gonna give him to me, hello, buddy. Hand me the towel because his claws are extremely sharp. Here. He will sit there and knead your legs and slice them to ribbons. Okay. Here we go. Come here, buddy.
Here's the cat.
Yeah, he's kneading my leg right now. Without 4 layers of towel over it, he would be slicing my leg. El gato, yes. He's a nice one. Look at this guy here. Yes. Not our cat. He just really likes us. All right, see you. All right. I was prepared though. That's why I had the towel here. Okay. So. All right. All right. So we are missing a main. You can't build an executable without a main, and so this is a linker error saying we couldn't find a function called main. If I come in here and have a main, that's cool. What if I had two mains? What if I had two functions that are both mains? Well, that won't compile. But if you had two different mains and two different .o files, you'll get a duplicate reference error. So for example, if I were to come into become curly and cd into milestone, I don't even need to do that. If I come over here, cd into milestone, benchmark, what is it called? Benchmark one. What's the name of the assignment I'm giving you guys? Oh, this is on the old server. Okay, never mind. Some of my directories have a generator, and then what a great naming system, huh? All right, so inside of here, yeah, I got one file here. It's got a main.cc in it. Here's another one that has a main.cc in it. Here's another one that has a main.cc in it. And so if I were to just try compiling g++ star.cc, then I will get a linker error because I have multiple definitions of main, right? So this one, generator.cc line 9, defined there. I got another one here, got another one here. You guys understand? So if you have multiple copies of main, you will get a linker error. This is not a compile error. This is a linker error, okay? A preprocessor error is different from a compiler error, which is different from a linker error. Sometimes people will just say casually, they'll say a linker error is a compiler error, but technically it's a different sort of thing. Okay. All right, so like I said, if you want to save the results of your compilation, you say g++-c. -c will save the results of your compilation into a .o file. And then when you want to link everything together, you can say g++ star.o, and that'll link all the .o files together. Or you can just list the .o files, link this .o file and this .o file together. So for example, let me go over to here, back up here, then main.cc. So let's do this. So let's say that square root of 2 is actually in a different file, and we want this to actually work now properly. Then what I can do is g++-c main.cc. That's going to partially compile it, works fine. Then I'm going to make a file called square root of 2.cc. Could you have main2? You could, yeah, but then it'd just be it'd be a regular function. It wouldn't. Main is the canonical entry point into your code. You can only have one of them. Okay, so for square root of 2, integer of double square root of 2 double x. We're going to approximate a square root of 2 by doing a for loop. For int I equals 0, I is less than or equal to I plus. If I times I is greater than or equal to x, return I. Okay, so basically, if we pass in 25 here, 5 times 5 is greater than or equal to 25, so it'll return 5. So we're gonna do a very terrible integer square root here. Now, if I tried compiling square root of 2, just normally square root of 2 normally, there's no main. And if I tried just compiling main normally, there's no square root of 2. So I have to put the two of them together. Okay, so the way that you do this is you partially compile one of them, and you partially compile the other one, and then you link them together, main.o and square root of 2.o. And now it works. So the square root of 6 is obviously 3. Because it checked 1, no. It checked 2, no. 3 is bigger than 6. There you go, 3. 3 is the answer. If we put in 100 here, then, now watch this. I don't have to recompile everything. The only thing I have to recompile is main, and then the linking step, where I link them together. And now the answer is 10. And if you're like, man, I wouldn't want to do that by hand, boy, it would be really neat if there was a tool called Make that would do all of this for me. You're in luck, because there is. You don't have to do any of this by hand normally. You have a build system, and the build system will figure out, oh, you changed main, let's just recompile main, and then relink the thing, and then we're good to go. You guys with me? This is what you have to do for lab time today. Okay? So, a Makefile has a format like this. You're going to see a bunch of lines in the Makefile that have this syntax. So it's a completely different language than C++, and it is kind of an ugly syntax. It was invented by a guy who needed a build system, and then he went on vacation, and by the time he came back, everybody was using it, so it was too late to change the syntax. So if you're wondering like why it looks just cobbled together, because it was, but we've been using it for 50 years now or something. Yeah, so all you do every time you update your file, you just type make. That's your build. Every time you change a .cc file, type make, and it will figure out what needs to be recompiled. Sartorelli, if you do make clean and make, you will do a full rebuild every time. So instead of a 3-second rebuild, you're going to be spending half an hour rebuilding it. My VR arcade game took 3 hours to full recompile. So we never wanted to touch anything that would trigger a full recompilation in the entire system. So, yeah, once I had a bug in the header file that everything included, and I'd make like one change and then hit make, and then I'd go to the break room and read newspapers for 3 hours. And then I'd go back, nope, that didn't fix it. Let me try this instead. Make. 3 hours. Nope. Go back in, change something else, make, I'm going home for the day. Bye. Then I come back in the morning. Hey, it worked. Cool. It was like absolutely miserable. When you're stuck in a loop where one change will trigger a 3-hour recompile, it changes the way you program. Like I said earlier, it changes the way you program. You stare at everything you do. You don't just like add a comment and recompile it. Oh, hell no. You stare at everything you do, double check, triple check everything, write a little bit, stare at it, Pretty good if you get paid hourly. Yeah, but it is painful. It is a painful process. Okay. So this is the syntax for Makefile. You have a target, something that's going to get built. This is a file that is going to get created. And it could be like a.out. A.out is a perfectly good target. We're going to build an executable named a.out. Then there's a colon. That's what separates the targets from the dependencies. And then you're going to have a list of files that a.out depends on. So for example, this thing that we are doing right here, a.out depends upon main.o and square root 2.o. In fact, let me make a makefile for you guys right now and just show you vim makefile. Okay, so we're building to automate the process that I just did here. So I'm just going to put main.o and square root 2 in there, and then the next line starts with a tab, and then after the tab, you put how do I go from the .o files to a.out, the line of code that you run. Okay, and so that line of code is g++ main.o square root 2.o, and that will build the a.out from. That's the linker step. That's that. A linking is like a puzzle piece. main calls this function, which calls this function, which calls this function. And this is in one .o file, and this is another .o file, and this is another .o file. And what the linker does is it finds all the different functions wherever they are and puts them all together into an executable. That's the linker step. If you call G++ on a bunch of .o files, it calls the linker LD under the hood. Okay, so now the question is, well, how do we get main.o? Main.o sounds like something we could use, right? Main.o depends upon which file. Which file produces main.o? What do you guys think? I'm going to wash my hands because I petted a cat. Be right back. You guys are correct. It is main.cc. Okay. And how do we go from it to the other? We type G++-C main.cc. Now, if we tried building our thing right, like a make clean from scratch right now, we're still missing one thing. Which thing are we missing? What do you think? What do we not know how to build in our build system currently? Square 2.0. Can spawn square 2.cc. We get from one to the other with this command right here. This is what you guys are going to be submitting for your lab time for your project. Okay. And then finally, we usually add a rule called clean. And clean has no dependencies. Any of these things can be built by typing make main.o, make square 2.0. If you don't type any target, it'll always default to the top one up here, unless you specify a different default. So if I type make clean doesn't need any dependencies. It's just going to run this program, and the program is rm-rf, a.out, and main.o, and square 2.0. Okay. So if I type make clean, it erases all my stuff. If I type make, you can see it compiles main, compiles square root 2, links them together, gives me an executable, and the square root of 100 is in fact 10. Okay, if I were to edit square root 2 and, I don't know, change something, return -1 instead, if it, I don't know. Watch what happens. If I type make, it does not need to recompile main. See? It only recompiles square root 2 and then uses the saved compilation. Main.o got saved in the previous one. It uses that saved compilation to link it together and make a.out. Okay? Does this make sense to you guys? It's extremely, extremely useful thing to know. Make is the Swiss Army knife of build systems, yeah. And there's a whole lot of more advanced stuff we could do with this. Probably the most useful, more advanced thing we could do is setting a variable. Because right now we're not setting any of our cool compile flags. Remember how we talked about that last time? So we could say something like cc flags is equal to stud equals C++ 26, turning debugging on, turning the optimizer on all the way, -f sanitize equals address, wall, and extra. That's good enough for now. And so you can make a variable inside of a Makefile like that. And then you can access the variable via cc flags like that. And then you can have all of your different compilation steps use the same flags without having to copy and paste them every time. So we will make clean, because if we just did a make, right, it's already up to date. So this is another use for make clean. When you change the compilation flags, it's unfortunately very common to have to rebuild everything. For example, if you want to turn address sanitizer on and off, I don't believe it works if some of them have it on and some of them have it off. I could be wrong about that, but I believe you have to do a make clean to get everybody on the same page here. So we're going to have to do a make clean and a make. And you can see now when it compiles it, it is compiling it with the compile flags that I chose. C++ 26, debugging information, optimizer, etc., etc. And we still get the same result here. Kind of cool, huh? Kind of neat stuff. Instead of G++, we can say cc equals G++. And do that instead. 3S $CC like that. And again, clean and make, and you can see this allows you to do something like change the compiler. Let's try a different compiler. Let's see if that makes a difference, right? So I'm changing it from G++ to Clang++, make clean, make, and now it's compiling it with Clang++ instead of G++. And all you have to do is change one line in your Makefile, and it changes the compiler used for all the different steps. You can't mix and match G++ and Clang++, I think. Pretty sure that would cause problems. Okay. Should we use those flags for your project? These are all pretty good flags for your project, yeah. Yeah, maybe not -03. That can make debugging a little bit more difficult because the optimizer will just come in and cut huge chunks of your code out. It's like, you don't need to do this, and it'll just delete your code. And so you're like looking at your code, and you're like, next line, and it just skips over like 30 lines of your code. You're like, oh, I guess that was all pointless. Yeah. My code is pointless, like me. What is the difference between Clang and G++? Short answer, nothing. Longer answer, they're completely different products. Under the hood, Clang and G++ are architected completely differently. Clang uses what's called LLVM, the low-level virtual machine, which allows, it's not actually a virtual machine in the sense that Java is, but basically, best way of putting this, you can have a bunch of different front ends that all, like, you can have a Rust front end and a C and a C++ and a, all these different computer languages. All of them can have different front ends, and then they convert into this assembly language that isn't real assembly language. And then you can have one optimizer that works on that stream of like a fake assembly code and optimize it away. And then it has a code generation backend that has code generators for x86 and ARM and x64 and things like that. And so it could produce executables for different architectures independently with any language, with any output architecture. And you can share a lot of the same optimizer code if you're doing Ada or C++. A lot of it can share the same kind of optimization. So from your perspective, you're not going to notice any difference between Clang and G++ most of the time, unless you're doing something like this where you're in C++ 26 zone, or 23. No, this is 23. Sorry. QA is 20, 2B is 23. Sorry. If you're in 23 mode and some things are implemented in G++, some things are implemented in Clang, you might notice some different features missing, if you're using one of them or the other. That's probably the biggest place where you're going to notice the difference, is just on the cutting edge. Until they get finalized, they're going to be rolling out features in the standard at a different rate from each other. So, yeah, make clean is like when you hit Shift F5 on a website and it just refreshes everything. Yeah, for sure. Clang also can be used as a language server. So if you guys are using NVim, NVim uses Clang under the hood. It probably doesn't make much difference to you. But like if I do something like that, something like that, if I do something like that, there we go. Then the language server picks up the fact that it's a problem and gives you see how it says Clang right here. Clang has something called Clang D that can run in the background and kind of like background compile your code. So that's another advantage that Clang has over G++. Which one generates the fastest code? Which one generates? It depends on the version and the test cases and things like that. So does that answer your question, Stevie? Should you use Cling? I don't know. Like I said, for where you guys are at right now for your project, you're probably not going to detect any difference between G++ and Clang. You're just not. If you want, you can benchmark it and see which one's faster. Some of them might compile faster. Some of them might generate faster executables. It could be a fun thing to experiment with. But like I said, in CSI 40 and 41, I'm not super concerned with maximizing performance. I'm more concerned with correctness, getting your code correct. Okay, so let's see. Is Minkrelli here? No, he's not. Okay, so let me go ahead and stop the. I guess this lecture will be on Makefiles, and then I'll record another one on Git.